Hi everyone. We now continue our lesson on statistical estimation, and this lecture is going to be rather dry.
We're going to be looking at distributions that are related to the normal distribution in some way. To begin with, we will look at the gamma function, which is an important special function, and we'll have a look at an associated distribution, the gamma distribution. Then we look at a special case of the gamma distribution, namely the chi-square distribution, and then another distribution which is obtained from the normal distribution and the chi-square distribution, namely the t-distribution. The reason we look at this is as follows. If you take a sample of independent draws from the normal distribution, then the sample mean and the sample variance are also random variables. Their distributions are related to the t and the chi-square distribution. We will need this later when we start looking at confidence intervals for means and variances. So let's begin by looking at the gamma function. It's denoted by this symbol over here, which is the Greek letter gamma, capital gamma. And it's a function which occurs frequently in statistics and in fact in mathematics in general. It's an important special function. It's defined as an integral from 0 to infinity of u to the x minus 1 times e to the minus u du. So here u is the variable of integration and x is the input variable that we put into the gamma function. Now most of the properties I will leave as exercises. For example, gamma of 1 is 1, and that is reasonably easy to see. If you take x is equal to 1 and you put it into the integral, then you have u to the 0 times e to the minus u du, and so you just have the integral of e to the minus u from 0 to infinity, and that's easily seen to be equal to 1. Using integration by parts, you can prove that gamma x plus 1 is equal to x times gamma x. In other words, we have a kind of recursive relationship for the gamma function. In particular, if n is a positive integer, then gamma n is just n minus 1 factorial. To see this, for example, let's have a look at gamma 2, which is gamma of 1 plus 1. So here x is equal to 1. And if we then look at gamma 1 plus 1, we get 1 times gamma 1. So gamma of 2 is equal to 1 times gamma 1, that's 1 times 1, which is 1. Gamma 3 is gamma 2 plus 1, which is 2 times gamma 2, which will be 2 times 1, which will be 2. Gamma 4 will be gamma 3 plus 1, which is 3 times gamma 3, but gamma 3 was 2, so it's equal to 6, etc. So the gamma function is a function which is like the factorial function, but it's defined for all x and not just for positive integers. It can be shown, for example, and this is another exercise, that gamma of a half is equal to the square root of pi. You will use the variance of the normal distribution to prove this fact. Here is a graph of the gamma function. I said that it is defined for all x, but that's not quite correct. It's certainly defined for all positive values of x, not just positive integers, and it's also defined for most negative values of x. However, at 0 and at all the negative integers, there are asymptotes. In other words, the function blows up, goes to positive infinity or to negative infinity at every negative integer. Try plotting this in MATLAB yourself. The gamma distribution is a distribution with two parameters, lambda and alpha, and it has a probability density function that is defined as follows. F of x is lambda to the alpha over gamma alpha times x to the alpha minus 1 times e to the minus lambda x. And this is the case for x greater or equal to 0. For negative x, the density is 0. The MATLAB function gam_pdf outputs the gamma PDF. Here alpha is the so-called shape parameter and lambda the rate parameter. The shape parameter influences the shape of the PDF. Here, for example, we have a case where alpha is equal to 1, which is exponential. Alpha is equal to 0.5, which looks a little bit hyperbolic. Alpha is equal to 10, and alpha is equal to 4. In each case, lambda is equal to 1. The rate parameter influences the rate at which events happen. However, in many software packages, they use a scale parameter instead of a rate parameter, and the scale parameter theta is defined to be 1 over lambda, in other words 1 over the rate parameter. MATLAB, for example, uses the scale parameter instead of the rate parameter. So if you're asked to output the gamma PDF with shape parameter 2 and rate parameter 5, you must put in the parameters 2 and 1 over 5. Whatever computing software you use, you need to check which version of the gamma distribution they have implemented. Are they using scale or are they using rate? Consider now the gamma distribution with shape parameter alpha equal to 1 and rate parameter lambda. Its PDF is just given by lambda to the 1 over gamma 1 x to the 1 minus 1 e to the minus lambda x, and that simplifies to lambda e to the minus lambda x. Now that's a density function that you ought to recognize. It's just the density of an exponential distribution with parameter lambda. Now recall that the exponential lambda distribution is often used to model the arrival of independent events such as defaults or catastrophes when the expected number of arrivals per unit time is lambda. Now in order to get a handle on the gamma distribution, we consider its moment generating function. Recall how a moment generating function is defined. The moment generating function of a random variable evaluated at a point theta is by definition the expected value of e to the theta x. Now this expectation can be written as an integral e to the theta x multiplied by the density of the gamma random variable capital X. We will integrate from 0 to infinity. We don't integrate from minus infinity to infinity because the density function is defined to be 0 between minus infinity and 0. Now we change the variable to u is equal to lambda minus theta x, and we simplify a bit, and it will turn out that the moment generating function of x at the point theta is equal to lambda over lambda minus theta all to the power alpha. This is something that you should just verify yourself. The computations here are not particularly difficult. Once we know the moment generating function, we know that we can find the mean, the variance, the skewness, kurtosis, etc. simply by differentiating the moment generating function. For example, the first derivative of the moment generating function is d by d theta of lambda over lambda minus theta to the alpha. In other words, we differentiate this expression over here with respect to theta, which means the alpha comes down, and we get this expression over here. And then the mean is obtained by substituting theta is equal to 0 into the moment generating function, which means that the mean is given by alpha over lambda. Similarly, the second derivative can be obtained from the first derivative by differentiating that with respect to theta, which means this alpha plus 1 comes down. This shows that the second derivative is just equal to alpha times alpha plus 1 over lambda squared. Now the variance is given by the second derivative evaluated at 0 minus the first derivative squared, also evaluated at 0, and so that is equal to alpha over lambda squared. As an exercise, you will show that the skewness can be given as 2 over the square root of alpha, and the kurtosis is 3 plus 6 over alpha. Now recall two facts about moment generating functions. Firstly, if two random variables x and y have the same moment generating function, then they must have the same distribution. Secondly, if x and y are independent random variables, then the moment generating function of their sum is equal to the product of their moment generating functions. This follows quite easily from the definition of moment generating function. The moment generating function of x plus y at the point theta is, by definition, the expectation of e to the theta x plus y, which factorizes as the expectation of e to the theta x times e to the theta y. But x and y are independent, so we can split this expectation, and each of these expectations is a moment generating function. Suppose now that we have two independent random variables x1 and x2, which are each gamma distributed. x1 has the distribution gamma alpha 1 lambda, and x2 has the distribution gamma alpha 2 lambda. So x1 and x2 may have different shape parameters, but they have the same rate parameter. Consider now the moment generating function of x1 plus x2. By the result above, the moment generating function of the sum is the product of the two moment generating functions, and we've seen earlier that the moment generating function of a gamma distributed random variable looks like this. Hence the moment generating function of the sum is of the same form with a different exponent. Now this looks like the moment generating function of a gamma random variable with shape parameter alpha1 plus alpha2 and rate parameter lambda. And hence by this first fact that I asked you to recall, x1 plus x2 must be distributed according to gamma, alpha1 plus alpha2 and lambda. Thus the sum of two independent random variables with the same rate parameter is also a gamma random variable. Next, we consider the chi-squared distribution. This here is the Greek letter chi, spelled like this, C-H-I. Suppose that z1, z2 up to zn are independent standard normal random variables. In other words, they have mean 0 and variance 1. Consider the random variable v, which consists of the sum of the squares of those normal random variables. V is equal to z1 squared plus z2 squared all the way up to zn squared. The distribution of v is called the chi-squared distribution with n degrees of freedom and is denoted by chi n squared. Suppose now that x is equal to z squared. It's just a sum of one square of a normal random variable, so it's chi squared with 1 degree of freedom. Then its cumulative distribution function is given as follows. The probability that x is less than x, that's the probability that z squared is less than x, which is the probability that z lies between the square root of x and minus the square root of x. And that simplifies as twice phi square root of x minus 1, where phi is the cumulative distribution function of a standard normal random variable.
Let's see why. Here is the probability density function of a standard normal random variable shown in blue. And the probability that z is greater or equal to y is just the green area. By symmetry, that's equal to the orange area, which is the probability that z is less than or equal to minus y. So the probability that z is less than or equal to y is the complement of the probability that z is greater or equal to y, and therefore it is equal to 1 minus the probability that z is less than or equal to minus y, which we can rearrange to say that the probability that z is less than or equal to minus y is 1 minus the probability that z is less than or equal to y. So the probability that z is less than or equal to y minus the probability that z is less than or equal to minus y is equal to the probability z less than y minus 1 minus probability z less than y, which simplifies to 2 times the probability that z is less than y minus 1.
If we then take y to be equal to the square root of x on the previous slide, we get the result. Now this is just the CDF of the random variable x equals z squared, and if you differentiate the CDF, you get the PDF. So the PDF of x, in other words the PDF of a random variable which is chi-squared distributed with 1 degree of freedom, is given by twice the derivative of phi evaluated at the square root of x times the derivative of the square root of x, which is a half x to the minus a half. Here we just use the chain rule to differentiate this expression over here. Now the derivative of phi prime, that's the derivative of the cumulative distribution of a normal random variable, is just the density of a normal random variable. And if you look at this carefully, this looks exactly like the expression in a gamma distributed random variable, where both the shape and the rate parameter are equal to half. Thus a random variable x equals z squared, in other words a chi-squared distributed random variable with 1 degree of freedom, is none other than a gamma distributed random variable with parameters a half and a half respectively. Now we have just seen that sums of independent gamma random variables are again gamma distributed. To be more precise, if we have two random variables that have shape parameters alpha1 and alpha2 and the same rate parameter lambda, then the sum of those two random variables is again gamma distributed with the shape parameter equal to the sum of the two alphas, alpha1 plus alpha2, and the rate parameter still equal to the same lambda. Now the chi-n squared distribution is equal to the sum of n many chi-1 squared random variables. The chi-1 squared distribution has an alpha of 1 over 2. So if we add up n of them, we're going to get n over 2. The rate parameter for the chi-1 squared is a half, and that stays the same. Now, since we know the density function of a gamma distribution, we now know the density of the chi-squared distribution with n degrees of freedom. We simply plug in alpha is equal to n over 2 and lambda is equal to a half. We can generalize this slightly. Instead of assuming that the random variables have mean 0 and variance 1 and are normal, we assume that they're normal with mean 0 and variance sigma squared. And then we say that the sum of those n many random variables has the chi-squared sigma squared distribution with n degrees of freedom. You can then show yourself that x has the distribution which is gamma with the shape parameter still equal to n over 2, but the rate parameter changed now to 1 over 2 sigma squared. From what we learned about the moment generating function of a gamma distribution, and I remind you the chi-squared distribution is a special case of the gamma distribution, we can see that the moment generating function of such a random variable is given as follows. It's lambda over lambda minus theta to the power alpha. Remember, lambda is equal to 1 over 2 sigma squared and alpha is equal to n over 2. And that simplifies. Simply multiply top and bottom inside there by 2 sigma squared. Now the mean of the gamma distribution was equal to alpha over lambda. That's n over 2 over 1 over 2 sigma squared. So the 2's cancel and therefore the expected value of x is just n sigma squared. Similarly, the variance was given by alpha over lambda squared, which in this case simplifies to 2n sigma to the power 4. The skewness was given by 2 over the square root of alpha, and the kurtosis was given by 3 plus 6 over alpha. Here we show the probability density function for the chi-squared distribution for various degrees of freedom. The chi-squared distribution with 1 degree of freedom has the curve shown in black here, which looks hyperbolic. With 2 degrees of freedom, that has alpha is equal to 1, and is therefore exponential, is shown in red. 3 degrees of freedom is shown in green, 4 degrees of freedom in blue, and 5 degrees of freedom in cyan. The next distribution that we consider is the t-distribution. Suppose that z is standard normal, and that u is chi-squared with n degrees of freedom, and that z and u are independent. Then the distribution of the random variable x defined to be z divided by the square root of u over n is called the t-distribution with n degrees of freedom. Where this comes from will be apparent very soon when we consider the distributions of the sample mean and variance of the normal distribution. The t-distribution with n degrees of freedom has the following probability density function, which we won't prove here. Again, the gamma function plays a role here. The moments of the Tn distribution are given as follows. Its mean, when it is defined, is 0. Its variance is n divided by n minus 2. Its skewness is 0, and its kurtosis is 3 plus 2 divided by n minus 4. Now note that the Tn distribution has moments only up to the n minus 1th moment. In other words, for example, the T1 distribution doesn't even have a first moment. In other words, it doesn't even have a mean. The T1 distribution is also called the Cauchy distribution. The T2 distribution will have a mean, but its variance will be undefined. The T3 distribution will have a mean and a variance, but it will not have a skewness. The skewness will be undefined, etc. We show here the probability density function of the T distribution for various degrees of freedom. In blue, we show the PDF of the Cauchy distribution, in other words, the T distribution with 1 degree of freedom. It has extremely fat tails, So fat in fact that its mean is not defined, even though it's beautifully symmetric around 0. The t-distribution with 4 degrees of freedom is shown in pink, with 15 in green, and the standard normal distribution is shown in red here. Now, as the number of degrees of freedom increases, the PDF of the t-distribution looks more and more like that of the normal. You can think of the normal distribution as a t-distribution with infinitely many degrees of freedom. Because the tails of the t-distribution are fatter than the normal, it's often used to model financial returns in preference to the normal. Now let's see why we introduced the chi-squared and t-distributions respectively. First, recall that if x is normally distributed with mean mu and variance sigma squared, then its moment generating function at the point theta is e to the mu theta plus a half sigma squared theta squared. Now suppose that x1 up to xn is a sample of independent random variables with the same distribution, normal with mean mu and variance sigma squared. The sample mean, x bar, is defined to be 1 over n times the sum of the x's, and that is also a random variable because it's a sum of random variables. Moreover, it's also normally distributed, as we'll see now using the moment generating function. The moment generating function of the sample mean is by definition the expectation of e to the theta times the sample mean. But because the random variables are independent, the expectation of this product splits as a product of expectations. Each of these expectations is a moment generating function evaluated at a point theta over n. However, the random variables xk all have the same distribution, and hence they all have the same moment generating function, and so we're taking the same moment generating function multiplied n times. In other words, we're taking it to the power n. Now we have x here, not x bar, and it is a normal random variable with mean mu and variance sigma squared, and hence its moment generating function evaluated at the point theta over n is this expression over here, which is the same as the expression at the top, but with theta replaced by theta over n. And we must take that to the power n. And that simplifies to e to the mu theta plus half sigma squared over n theta. Now that looks like the moment generating function of a normal random variable with mean mu and variance sigma squared over n. And by the correspondence between moment generating functions and distributions, we can deduce that x bar is normally distributed with mean mu and variance sigma squared over n. In particular, if we subtract the mean and divide through by the standard deviation, we will get a standard normal random variable. In other words, x bar minus mu over sigma over the square root of n is standard normal. Typically, however, when we have a sample x1 up to xn, we do not know the actual or population variance. In other words, we do not actually know sigma squared. Instead, we approximate it by the sample variance, which is defined as s squared is equal to 1 over n minus 1 times the sum of the squares of xk minus x bar. The question now is, what happens to this distribution over here, x bar minus mu over sigma divided by the square root of n, when we replace sigma by the sample standard deviation? In other words, what is the distribution of the sample mean minus mu divided by the sample standard deviation divided by the square root of n? Moreover, we're also interested in the distribution of the sample variance. Now we're going to denote the sample mean and the sample variance of a sample of size n with subscripts. So x bar n and s squared n here indicate that these are the sample mean and variance of a sample of size n. Then we have the following result. The random variables x bar n and s squared n are independent. Moreover, their distributions are related to the t and the chi-squared distributions as follows. N minus 1 times the sample variance over sigma squared is chi-squared distributed with n minus 1 degrees of freedom. And the sample mean minus mu divided by the sample standard deviation divided by the square root of n is t distributed with n minus 1 degrees of freedom. These results will become important when we consider confidence intervals for the sample mean and sample variance of a sample of normally distributed random variables. later on. Now, I'm not going to go through the proof of these results. However, for those of you who are interested, they are on the slides here. Notice that these slides all have a title that is start. In other words, you don't need to go through this, but if you're interested, the results are here. Now let's have a look at confidence intervals for means and for variances. We begin with confidence intervals for the means based on the t-distribution when the data is normally distributed. Recall that if we have independent identically distributed samples from the normal distribution with mean mu and variance sigma squared, x1, x2 up to xn, then the quantity over here is t-distributed with n-1 degrees of freedom. Here x bar is just the sample mean and s squared is the sample variance. Now if we let t to the -1 of n-1 denote the quantile function of the t-distribution with n-1 degrees of freedom, then we obtain that x bar plus or minus that quantile times s over the square root of n are the endpoints of a 1 minus alpha times 100% confidence interval for mu. In other words, you need to be able to compute the quantiles of the t-distribution at the 1 minus alpha over 2 level in order to work out the confidence interval. Now in MATLAB that can be done with the function tinf p nu, which computes the quantile function of the t-distribution with nu degrees of freedom at the point P. Note, however, that this gives an exact confidence interval only if you know that the data points x1 up to xn are actually independent, identically distributed and normally distributed. For large n, we know that the t-distribution and the standard normal distributions are approximately the same, so there will be very little difference between the t and the normal confidence intervals. Consider the following example. We generate data from the standard normal distribution. We then compute the confidence intervals for the population mean using both the t-distribution and the normal approximation. We start with a very small sample, a sample size of 4. We generate data from the standard normal distribution, in other words 4 data points. We find the sample mean, the sample standard deviation. We want a 90% confidence interval, so we take alpha to be 0.1, in other words 10%. In order to compute the normal confidence intervals, we find the normal quantile at the 1 minus alpha over 2 level. We compute the lower value, which is x bar minus the quantile times s over the square root of n. Similarly, the upper is given as follows, and the confidence interval is given as the interval from L to U, which in this case is from minus 0.5 to 0.93. On the other hand, if we compute using the t-distribution, we're going to use the quantiles of the t-distribution with 3 degrees of freedom at the 1 minus alpha over 2 level, and compute L and U in exactly the same way, but using the t quantiles rather than the normal quantiles, in which case we get a confidence interval which is considerably wider than the one given by the normal distribution. Now remember that in this case, as the data is normally distributed, the confidence interval given by the t-distribution is the correct one, whereas the one given by the normal approximation is just an approximation. If we increase the number of data points, however, to say 250, the difference almost disappears. As you can see, the confidence interval is now much narrower, and moreover, the confidence interval suggested by the normal approximation and the one given by the t-distribution are almost the same. This is because the t-distribution approximates the normal as the number of degrees of freedom, in other words the number of data points, increases. Let's now find confidence intervals for the variance for samples drawn from the normal distribution. Suppose that x1 up to xn is a sample of independent variates drawn from the normal distribution with mean mu and variance sigma squared. Recall that in that case we know that n-1 times the sample variance over sigma squared has the distribution chi squared with n-1 degrees of freedom. If C alpha denotes the alpha quantile of the chi squared distribution with n-1 degrees of freedom, then we obtain that the probability that this quantity over here lies between C alpha over 2 and C1 minus alpha over 2 is just equal to 1 minus alpha. Rearranging, we see that n minus 1 times s squared over C1 minus alpha over 2 is a left endpoint of a confidence interval, and n minus 1 times s squared over C alpha over 2 is the right endpoint of a confidence interval, and that is a 100 times 1 minus alpha % confidence interval for the variance sigma squared. To compute these alpha quantiles for the chi-squared distribution, MATLAB has the function chi2inf pv, which computes the chi-squared quantile function with v degrees of freedom at a point P. Notice that this confidence interval is not symmetric about s squared. In fact, recall that the chi-squared distribution isn't symmetric. Consider the following exercise. This is exercise number 4 from the class exercises. You have just 10 independent draws x1 up to x10 from the normal distribution with mean mu and variance sigma squared, but you don't know that mean and you don't know the variance. The mean of your sample is x bar is equal to 0.93 and the standard deviation of your sample is s is equal to 1.05. Using the following table of quantiles, compute a 90% confidence interval for the mean mu and for the variance sigma squared. So in this table we have the t-distribution quantiles with 9 degrees, 10 degrees and 11 degrees of freedom. We have quantiles of the normal distribution and we have quantiles of the chi-squared distribution also with 9, 10 and 11 degrees of freedom respectively. We're told that x bar is 0.93, that s is equal to 1.05 and we've got 10 data points. We want a 90% confidence interval, so alpha is equal to 0.1. Now, in order to produce a confidence interval for the mean of data drawn from the normal distribution, we need to use the t-distribution with n minus 1 degrees of freedom. So we are interested in this row over here. Furthermore, we want alpha is equal to 0.1, so 1 minus alpha over 2 is 1 minus 0.05, that's 0.95, and hence we're interested in this quantity 1.833. So the t quantile we're interested in is 1.833, and the confidence interval is then given as follows. It's x bar minus the quantile times the standard deviation over the square root of n, and similarly x bar plus the quantile times the standard deviation divided by the square root of n, and we get a confidence interval that is from 0.32 to 1.53. In order to work out a confidence interval for the variance, we need to use the chi-squared distribution, and since n is equal to 10, we need the chi-squared distribution with 9 degrees of freedom, in other words this row over here. Because the chi-squared distribution is not symmetric, we need both the 1 minus alpha over 2 quantile, which is 16.919, and the alpha over 2 quantile, which is 3.325. And so we define both of those quantiles, and so the confidence interval for the variance is given as n minus 1 times the sample variance divided by the 1 minus alpha over 2 quantile, and on the other side n minus 1 times the sample variance divided by the alpha over 2 quantile, and that's equal to the interval from 0.58 to 2.98. You can also check this by using the built-in quantile functions. In this case, they will give us exactly the same answer.